Hi everybody, welcome back to the Feynman Technique. Today we're going to be finishing our work that was started with this integral. This is a generalized Mellin-Barnes integral, and now we're going to generalize it even more. So this is as general as one of those integrals gets. Obviously, with the exception of the bounds need to be 0 to infinity. But we'll be extending this basically. In my last video, I showed that this was true. I will post a link to that video in the description. So I guess let's just get started. So what we're trying to do is we're trying to just get one final integral formula for any integral in this form where C, D, S, T, and U are just arbitrary constants. And obviously, the arbitrary constants need to be such that this integral converges. Okay, so let's go. All right, what do? Well, we need to somehow get it into this form. So the first thing I would like to do is make a substitution so that this is just y. So we're going to let tx raised to the d power equal y. All right, well, this is going to imply, let's solve this for x. Okay, so we'll divide both sides by t. And then we will raise both sides to the 1 over d power. It will give us x over here. All right, and now we'll solve for dx. So dx, all right, that's going to be, let's see, we bring down this power. We subtract 1 from the power. And then we multiply by the derivative with respect to y of this, which is just going to give us times 1 over t dy. All right, and this substitution will not change our bounds of integration. So now let's plug these things in. Okay, well, first of all, the whole point of it, the substitution, was so that we could let this be y. All right. S is not going to change, so let's just go ahead and bring it outside of our integral. All right, our x, well, that becomes this. With our substitution, our x is just this. Okay, and then we can bring this c inside like this. All right, let's get rid of these parentheses. And then you can see we could bring out a t to the negative c over d. So a t to the negative c over d. That will take care of this t right here. All right, and then our dx is this. And you see we performed the substitution correctly. Let's go ahead. Let's see. We can bring this. We can combine this with this right here, and bring it all out as a t to the negative 1 over d. So negative 1 over d, and then we don't need this, and we don't need this. All right, well, let's see, we can combine our y terms. So this is going to be y to the c over d plus 1 over d minus 1. And again, we can bring out this d right outside our integral like that. All right. Let's see. Now, I don't like this mess right here. We could call this some other constant, but I think what I'm going to do is I'm just going to call some new constant this. And I'm going to actually write this as C plus 1 over D. All right. So now let's just make some other arbitrary constant, V, that's equal to C plus 1 over D. So now what do we have? We have that I should be labeling our original integrals. We're going to call this I. So I is equal to that, I is equal to this, and I is equal to this. Okay, but this C plus 1 over D is just V. So now we just have a V minus 1 here. Okay, so our next step, we are going to divide the top and the bottom by U. All right, so divided by U, and then dividing the top by U, we'll just go ahead and put a U down here. Okay, well, obviously this is 1. All right, so now let's perform a new substitution. We'll let some new variable equal this. We'll say that Z, I'm not calling it a complex number, it's just a new variable name. Z is equal to Y over U. This, of course, implies that Y is equal to Z times U, which in turn implies that dy is equal to U dz. All right, let's perform that substitution. All right, our y is, parentheses, the u. Our y over u was specifically designed to be just z. And our dy is just u dz. All right, so let's bring this u, of course, is going to cancel this u. And then we can break this up into two separate exponentials. One of them is u, and the other one is z. All right. And then this u to the v minus 1, of course, can just come right outside our integral. I'm just going to get rid of as much of this as I can. So we'll cut that out from the inside and just put it there. Okay, we are getting very close. Now, this integral right here is in a form that we can just plug in to this formula up here. All right, so I'll copy, well, actually, I'm going to cut it and paste it down here. All right, let's see. I'm going to change this dummy variable to x. All right, so let's see. Our a is v minus 1. So v minus 1 plus 1 is, of course, just v. Let's see. And our b is just 1. So our b is just 1. So this is true, which means that we can multiply it by this constant on both sides, and it is still true. Now don't forget, this is equal to I, which is also equal to this. So, all right. So now we have it. Now we have that this is equal to this. Now we still need to clean up a little bit. Let's go ahead and let's see. We made a substitution. V was equal to something, or something was equal to V. So our V, don't forget, is just this. So let's put our V right here. and right here. All right, and now let's do some cleanup. Let's see. I think. All right, let's see. Let's put a parentheses around this and factor out a negative. And then we'll have, it looks like 1 plus C over D. 1, well, we'll call it C plus 1 over D. And then let's call this one D over D. So we can just have a C minus D plus 1 all over D. Let's see. Let's just take this S out front. Let's take this right here and put it right here. Let's take this pi and put it out front. And let's just make this an S over D. Okay, I think this is there anything else I could do to clean this up anymore? I don't think so. I think this is going to be how I leave it. All right, now let's just check. Let's just check. I'm going to bring these all the way up to the top, and then I'm going to modify our arbitrary constants here. Let's try changing the value of C. And of course, once C gets over 2, it looks like it becomes undefined. Why would that be? Probably because of the difference between C and D. You'll see this thing is not going to converge unless our D is at least 2 more than our C. So let's increase our D here, and then you can see we can drag that C up to, well, actually it needs to be at least 1 more than our C. Great. And then let's try changing the value for S, and yeah, that's gonna work. Okay, it looks like it's getting a small difference here, but that's just due to Desmos having to evaluate this integral numerically. Let's try changing some values of T. Yeah, let's try changing some values of U. Okay, yeah, they match up pretty closely. But it is true. We did all the stuff correctly. So finally, we just have this. This is true. This integral, as long as it does converge, is going to converge to this. So never again on this channel will I be solving an integral that is in this form. I'm just going to be using this formula right here. Integrals like this can take a long time to solve, and it's nice to have just one master formula for it. But anyway, there you go, guys. Hope you enjoyed that, and we'll see you next time.